Hello, this is Andy Schweitzer covering some basics on atomic structure. Some of this stuff you may have had in previous science classes, so we'll be going relatively quick through it, highlighting some of what I think are the most important parts of atomic structure. Atomic structure will eventually lead towards periodic table trends, which will lead eventually towards bonding. So there are some important aspects to what is actually here. So the first thing we have listed here is the atomic number. Now, an atom obviously has protons. An atom has neutrons. And an atom has electrons, usually. So, in the atom, it's important to know what things have what charge and what they mean. The protons have a mass of 1 AMU. AMU stands for atomic mass unit. You could convert an AMU to kilograms. It's just another unit of mass. It's set up to handle that of a proton. A neutron has a mass slightly more than 1 AMU, but it's usually considered 1 AMU. And electrons have very, very small amounts of mass, generally considered to be zero mass. It's about 18/40th of a AMU, 1,840th of an AMU. So it's tiny, and if you have lots and lots of electrons, you could add up to a number greater than 1 AMU, but in that case you usually have another whole lot more of these protons and neutrons, so technically that amount of mass again drowns it out. So the atomic number is the number of protons. It is how we order the periodic table. Hydrogen has 1 proton. Helium has 2 protons. Lithium has 3 protons. It determines the element. Okay. Our second aspect here would be the mass number. And the mass number is, let's flip to the next thing here, slide here, would be the protons, which have 1 AMU. We have the neutrons, which also contain 1 AMU. So all this mass is located in a very small center of the atom called the nucleus. There's a lot of area around the outside that we would call the electron cloud, and I'll just represent it by little dashes here. There is no one model that we have, at least easy looking models, that might describe the atom fully. Just patchwork of different things, and in this case the outer section of this particular guy, I would say just this outer area here, is all electrons, and there is essentially no mass in that area. So the majority of an atom is quite empty. This was originally isolated by Rutherford's gold foil experiment. He took a piece of gold foil, which has the unique ability to be made very thin, and he essentially it's a weird looking drawing. I thought I could do 3 dimensions, but essentially it's a 3-dimensional little scoop. He took a piece of block of lead, and he was more a physicist and dealt with a lot of things involving radioactivity. He coined the word half-life, shot alpha particles at this thing, and realized that the majority of them went through, but did have a few that got kicked back. And this determined, he came to the idea that the majority was empty space. These alpha particles would shoot through, and occasionally one would hit this nucleus and reflect back at its detector. Either way, all the mass is located right here, so we call this the mass number. The mass number is equal to the protons plus the neutrons. It's the mass of a single atom. Of course, as we move on to learn more and more about some of these things, you'll realize that different atoms of element have different number of neutrons. So the individual mass of a given element can vary because of the number of neutrons can vary. So we'll talk more about that just in a moment or two here. But either way, the mass number tells the mass of a given element. This is not on the periodic table because no one single element, even though they have the same number of protons, these can vary. Okay. The next one, again, right off this topic, is average atomic mass. Now, again, we have protons for a given element, and let's say we have, let's go with something small, let's say boron. Boron would contain, based on the periodic table, 5 protons. And it also has some number of neutrons. Sometimes it's listed like that. Either way, it could have 5 neutrons, which give this thing a mass of 10 AMUs. But it could also, boron could potentially have 5 protons and maybe 6 neutrons. This would give it a mass number of 11 AMUs. Now, the Earth seems to be pretty evenly mixed. I mean, if you were to grab a sample of boron in America versus China, whatever, it seems to be like it's evenly mixed. There's random mixtures of different isotopes, and these are I should phrase it, these are called isotopes. So in nature, there's a blend of these, and they come up with an average weight. In this case, the average weight, and there might be more than just 10 and 11 for boron. I'm not going to. You could look it up on internet and see what actual isotopes are available, but the average is 10.81 AMUs. Now that means that the number of protons is going to be 5, all right, and the number of neutrons is 6.81 on average. Okay, that means some might be higher, some might be lower, but the protons are definitely locked at 5. But we use this a lot. It's the average atomic weight. It's how much exists. It's average of all isotopes in nature. Sometimes it's 10, sometimes it's 11, but on average, 10.81. Again, to fully understand that takes a little thought, but it's like an average grade. Okay. I also would state that the AMU is also used is 10.81 grams per mole. Just a heads up that a mole, which is 6.022 e to the 23rd. If you're watching this and don't know what moles are, well then you can ignore this. But in this case, they picked out a mole as being a number of particles to match up with an AMU, so that the 10.81, which could be AMUs, also equals grams. So keep that in mind. All right, so charge. The question might be, okay, how does them acquire charge? What does charge mean? Well, a proton has a positive 1 charge, a neutron would have no charge, and an electron has a -1 charge. So even though as a scientific community we really don't know what charge really is, it's either plus or minus. We don't know. We know that positives repel and negatives repel, but positive and negatives, they will attract each other. We know that this attraction is really what drives all chemistry. So, for example, an oxygen atom, generally speaking, would have 8 protons, and it will have 8 electrons, and that would make it essentially a net 0 charge. It has a possibility here where maybe because of the structure of the atom, for a particular atom to pick up more or lose electrons in order to acquire a certain stability. Oxygen has the ability to form a -2 charge, and we'll learn more about that in upcoming videos. But in this case, it still has its 8 protons, and now it has 10 electrons. I look at it like this. We have 1, 2, 3, 4, 5, 6, 7, 8 protons, and we have 1, 2, 3, 4, 5, 6, 7, 8 electrons, and 2 more electrons to boot. So they cancel all the way down, and leaving 2 net electrons left, which is a -2 charge. So for negative 2 means we have 2 more electrons than protons. If looking for mathematics, charge equals the protons minus the electrons. So that would be 8 minus 10 equals a negative 2 charge. And that's basically all charge works. How does an atom acquire charge? Now this is getting a little more complicated, but is definitely something that you should be aware of, in the sense that if I have, let's say, an oxygen atom and it goes to, let's say, an O negative 2 charge, in this case this guy has 8 protons and it has 8 electrons. This guy here has 8 protons and this guy has 10 electrons. So this guy gained 2 electrons in this process. The number of protons is locked. It's in the nucleus. Unless we do a nuclear chemical reaction, we're either going to be gaining, in this case we are gaining electrons. Okay, and a fancy dancy term for that is reduction. Sounds strange that gaining is reduction, but that's what it is. As opposed to if we have two F negatives going to, let's say, an F2 molecule with no charge. In this case, there's 2 molecules there. Each of them contains 9 protons, and each of them contains 8 electrons. That's why they're each negative 1, going down to the point where each of them contains 9 protons. And let me back up a second here. I should do this. Because it's negative 1, it would be 10 electrons. 10 electrons. Alright. As it goes neutral, we're going to have 9 protons and 9 protons, and of course 9 electrons and 9 electrons. So this guy, this is before snapshot, after snapshot, same chemical. It goes from having 10 electrons now having 9 each. So it needs to get rid of 2 electrons, 1 each. This is losing electrons, which is a fancy term. To lose electrons is oxidize. Okay, so we'll stop there. A couple important points there.